Golden section search. This is a very fast and efficient way to close in on an extremum. So we'll step through the method by illustration, summarize the method, make some notes about it, and at the very end, derive this magical golden ratio number that's used in the algorithm that makes us incredibly efficient. And unfortunately, what I can't get into is more of a history of the golden ratio and all of the places in nature and science that this comes up. It's a quite magical number, and I think you'll see how that's magical for optimization here. Description of the method. So let's start out with some function. And the first thing we want to do is choose a lower and an upper bound that span the extremum. So we have some position we're calling x sub L for the lower bound, some position x sub U we call the upper bound, and we're going to be operating between these two bounds. Now, we have to assume that there is only one extremum between those bounds. If somehow we've goofed and there's multiple, well, this method can fail. So that's where we start. We pick our bounds. The next thing we need to do is evaluate the function at the bounds. Now, to really appreciate optimization and how this is improving things, usually this function call is a very expensive one. Imagine every time you evaluate a single number, it takes 1 day. So right here we have 2 days of calculations simply to evaluate the function value at 2 points. So keep that in mind and you will appreciate why we want to minimize the number of iterations in this algorithm, minimize the number of times we call that function. Okay, so we now have our bounds and we've evaluated the function value at those bounds. At this point, we want to calculate two very special intermediate points, and we'll get more into later of why this is magical, but I'll touch on it in a few slides. First, we'll calculate this golden ratio. We'll actually derive this at the end, but it's about 0.62. Once we calculate this golden ratio, we will calculate a distance d. So we will look at the span from our upper to our lower bound, and we'll multiply that by the golden ratio. And then we'll simply come up from the lower bound by the distance d and down from the upper bound by a distance d, and we will have these two magical intermediate points. We will call these two intermediate points x1 and x2. And we're labeling that right here. Once we have these 2 points, the next thing we will want to do is evaluate the function at those 2 points. Keep in mind, calling this function can be a very complex, time-consuming operation. So for us, this is taking 1 day. So we now have added 2 more days to our algorithm. Everything else was lickety-split fast, but evaluating that function was really slow. We've called it 4 times, so that was 4 days of computation. We don't want to have to redo those, or we want to minimize the number of those function calls. Okay, so we now have 4 points, and we've evaluated the function at all 4 of these points. Now we would like to decide where between these bounds, where within these 4 points is that maximum. So we're looking for a maximum. So we check and compare F1 and F2. And if F1 is less than F2, which it is now, that means the extremum has to be to the right-hand side of all of these points. If this were reversed, if F1 were greater than F2, that would mean the extremum is sort of to the left side of these 3 points. But in our case, F1 is less than F2, so we can say that the maximum is to the right, or on the right-hand side of our points. So we'll add a highlight to that. So the extremum is now somewhere within this gray region. So our next step is to move our bounds in towards this new range that we've highlighted. So we're going to adjust the points to close in on that maximum. One of the first things we do, we had a lower bound somewhere down here. We will move that up to where the previous x1 intermediate point was. So what was x1 now becomes the new lower bound. Well, we already know what x1 was. We already know what the function was at f1. So we just copy that information over to the lower bound. We do not have to evaluate the function again at the lower bound, and it would be a huge mistake to do that. The algorithm would still work, but it would be very, very long, and it's not necessary because we calculated this at the previous iteration as f1. So we just copy that over as fl. The other thing we did, the old x2, we copy over and make it the new x1. So again, we're just copying information over. We're not calling that function again. And the upper bound remains the same. So the question is, where is this new 0.2? What do we do with that? So that's our next step. Let's calculate where that new intermediate point is. We just sort of put a green line in here to represent this is where it will be, but where exactly is that? We've already calculated the golden ratio R, so we don't need to do that again, but we'll calculate this distance D, and it's the golden ratio times the span between the upper and lower bounds. And so what we'll do is we'll come up from the lower bound by the distance D, and we will have x2. Now this is a new point, so we will have to evaluate the function at that point. And that's what we do here. So this is now 5 days of computation for us. But one of the huge ahas, we went through an entire iteration, but we only had to evaluate that function at one new point. We had to start by setting everything up and evaluating at 4 points, but we went to our entire next iteration and only had to evaluate that function once. All the others were just copies from the previous iteration. We just copied the information over. So the only new function call was evaluating at this new intermediate point x2. So we're kind of back to where we started again. So we have this decision, where within this new span is the extrema? And so in this case, f1 is greater than f2. And so if f1 is greater than f2, the maximum has to be to the left. So we want to be somewhere in this span of points. If that were not the case, if f1 were less than f2, then the extremum would have been to the right. But that's not the case here. Our extrema is to the left. And so that's where we want to focus our attention. So we'll highlight that region. Our new maximum, or the maximum is to the left. So we want to adjust our interval to this new highlighted gray region. So that's what we do. We adjust our points. So the first thing we did, what used to be x2 is now our new upper bound. So we just simply copy all the information from the old x2 to the new upper bound. We do not evaluate this function again. Yes, the algorithm would work if you did that, but it would be hugely slow. We don't want to do that. So what used to be x1 now becomes the new x2. So again, we just copy the information over from x1 to x2. We don't evaluate the function call again, just copy the information over. And the lower bound stays the same. So now we have this problem. What is this new x1? Where would that go? So that's the next step. Let's calculate the position of that new intermediate point. So we'll calculate our distance, and it's the golden ratio times the span between our new upper and lower bound. So the x2, simply we come down from the upper bound by the distance d, and this is our new x1. Now that we know where x1 is, we now have to call the function and evaluate the function at the x1. But again, I'll point out, we've gone to a whole new iteration, and we only had to call that function once to evaluate it at our new intermediate point. All the other three were just copies from the previous iteration, no new function calls. So here we are with our new interval. Now we have to decide on the left or the right, where is the extrema? In this case, F1 is less than F2. So in fact, we know that the maxima has to be on the right side of our interval. That's where we want to focus our attention. And this repeats. We'll close the interval in on that. We will evaluate new intermediate points, evaluate the new function. And this keeps going and going and going. And we can illustrate this method for some number of iterations, but usually in 20 iterations or so, we can close in pretty accurately on an extrema. And so this is highly efficient because of where the new points lie relative to the old points. And we'll talk more about that. So how do we determine if we've converged? Well, we can look at the distance between the upper and lower bounds. And I like to average that to sort of normalize it. When that falls below some tolerance, we know that we've converged. So after the algorithm is over, one thing I like to do, just to give that another couple decimal points, I guess, of accuracy, I like to average the upper and lower bounds from the very final iteration, call that where the extrema is. In this case, it's a maximum, and then maybe evaluate the function. Maybe I'll just evaluate the function, or sorry, average the function at the upper and lower bounds. If it's not such a big deal, maybe I'll call the function again, evaluate it at that averaged extrema value for x. So at that point, the algorithm is done. Method summary. Let's summarize the method with a block diagram and step-by-step of what would happen. So the very first thing, of course, we have our function. We need to pick upper and lower bounds that span the extremum. We'll then evaluate the function at the bounds. Remember, this is the expensive part. That function call can take a very long time. It might be a simulation or some other complicated calculation. From there, we'll calculate two intermediate points. And these are magical intermediate points coming from this golden ratio. And then finally, we have to evaluate the function at those intermediate points. So at this point, we're sort of initialized. We came up with 4 points, and we evaluated the function at those 4 points. Now we go into our iterations. So we'll check if we're converged. If the span between the upper and lower bound is above a tolerance, then we need to keep iterating. So we need to figure out where within our span is the extrema. Well, if F1 is greater than F2, that means the extrema is to the left side of our interval, and we need to adjust our points. For the most part, we're just copying information over. The expensive thing is we're going to have to evaluate, we're going to have to call our function to evaluate it at the new x1. But that's all. Everything else is just copying information over. And then, of course, once that's done, we go now check the span between the upper and lower bounds and see if we've converged. Well, anyway, if this wasn't the case, we need to check the other way. What if F1's less than F2? And of course, if that is the case, then the maxima is to the right side of our interval, and we copy all our information over to from our old to our new points a little bit differently, following the equations here. The expensive thing is calling this function to evaluate the new function value at x2, at the new value of x2. Once that is done, then we can check the span between the upper and lower bounds, see if that's fallen below the tolerance. If not, we keep iterating. Now, to make a really robust code, we might even want to add, well, what if F1 equals F2? That's rather unusual, but if that happens, if it doesn't happen, then we keep iterating. But if it does happen, I would say the algorithm's over. We can really just average at that point x1 and x2 to figure out where the extrema is. It has to be symmetric between the two. And then we can average to calculate the function at the extrema, just average F1 and F2 because they're equal anyway. So anyway, we keep iterating this. This last case is very unusual, probably will never happen. If suddenly we fall less than our tolerance, so the distance between the upper and lower bounds is sufficiently small, we're done the algorithm, we will just evaluate one final point where the extrema is as the average of the upper and lower bounds, and if not too expensive, we will evaluate the function at this new extrema value. If it is an expensive call, I might just average FU and FL. But anyway, we're done the algorithm here. So that's the golden section search. If a picture's worth 1,000 words, an animation is worth 1,000,000 words. So here we are, iteration 1. We've calculated our 4 points, and we've evaluated the function at all those 4 points, and we've identified which side of this span of 4 points our maxima is on. It's on the right-hand side. So what we're going to do now is iterate how the points from the previous iteration fall into the points of the next iteration, and we'll work through several iterations. So here we go. We're going from iteration 1 to iteration 2. Notice how those points from the old iteration fall exactly on points from the old iteration. And so it's because of that we only have to evaluate the function at one new point, because 3 of the 4 from one iteration fall on the top of the 3 of the 4 the next iteration. So here's sort of a still version of what we just saw. Here is some iteration I, and we see that the span is to the, or the maxima is to the right. And so we adjust our points to the right. And here's the adjusted points. And I've drawn these vertical dash lines to show how points from the previous iteration fall on the points of the next iteration. And 3 of them are just copies. So we don't have to evaluate the function at those points. We just copy information over. There's only one new point per iteration. So that's the point I'm making there. Now, even more, every iteration, we only have to evaluate one new function, but every iteration, we've actually eliminated almost 40% of the span between the upper and lower bounds. That's huge. So this golden ratio has done all of this, and it's made this algorithm a very fast and efficient way to do optimization. Derivation of the golden ratio. There are many derivations of the golden ratio because it comes up all over in nature and science. Here we're going to derive it in the context of our optimization. So we have a picture to the left, and I'm sort of arbitrarily defining 3 different lengths. So we have L1 is the distance from the lower bound to x2. L2 is the distance from x2 to the upper bound. And then we have an L0, which is the span between the upper and lower bounds. So from this picture, we can see that L0 is xu minus xl because L0 is the span. L1 is x2 minus xl, and L2 is xu minus x2. So that's how the L's relate to the x's. At this point, we need to recognize that when we go from one iteration to the next, we want our points to lie on top of the previous points. And so we need some conditions that will ensure that. The first condition, we need to ensure that L1 and L2 cover the entire span. So L0 equals L1 plus L2. We got to do that. The next thing, the way we ensure that the lines from the new iteration fall on top of the lines from the previous iteration is we have to preserve the proportioning, if you will. So the way we'll do that is we'll say L1 to L0 has to be L2 to L1. And that will preserve the proportioning from one iteration to the next. So here's a repeat of our conditions that will ensure that 3 points from the previous iteration will fall on top of 3 points on the new iteration. So the first thing we'll do is we see that L0 is L1 plus L2. We will take this L1 and L2 and plug that in down here to replace L0. Now we have a single equation with only L1 and L2. At this point, we're going to define the golden ratio as L2 divided by L1. So we copy this equation from above, just a straight copy. Now we're going to do some algebra with that. The first thing is invert the equation. So we just swap numerator and denominator on both sides, and we end up here. Next thing we'll do is expand the left side. So we have an L1 over L1 plus an L2 over L1. And of course, the L1 over L1 is just 1 plus the L2 over L1. At this point, let's recognize that the golden ratio L2 over L1, so this term is the golden ratio. This last term on the right-hand side is 1 over the golden ratio. So we now have an equation with all r's. At this point, we're going to multiply both sides by r and then move all the terms over to the left to simplify, and we have a very simple polynomial. And we will solve that on the next slide to get the value of r. Okay, so we have a polynomial to solve. Let's remember the quadratic formula. So ax squared plus bx plus c equals 0. If we can put our equation in this form, here's how we will calculate its solutions. And there's two solutions because there's a plus and minus here. Well, from the previous slide, this is exactly what we had. So in this case, our A is going to be 1, our B is going to be 1, and our C is going to be -1. So we take those values for A, B, and C, plug it in up here, and we'll have our answer for R. So that's exactly what we do. And if we work the math, we end up here. We have a -1 plus or minus square root of 5 divided by 2. So what do we do with the plus and minus? Well, we would like R to be positive. That means we have to take the positive here because we took the negative, we'd have a negative R. So let's take the positive, and that is our golden ratio. And if we do the math, it's 0.618033988, and so on. So that is the golden ratio. And that's what does all the magic in this algorithm for optimization. Pretty incredible method, actually. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.